Good evening. I'm Alexander Rose. I'm the executive director here at Long Now. One of the things I wanted to talk to you a little bit about tonight is our new newsletter that some of you members may have seen. How many people are members here? Awesome, thank you. How many people are guests of members here? Oh, nice. You guys should all become members. The newsletter has been put together by our staff and particularly Ahmed, who had written for our blogs quite a bit. Awesome, we have an Ahmed fan group. But what we're trying to do is bring some of the other projects around long-term thinking from around the world, as well as some of our own content together in a place where we also do, in some cases, some original writing and bring some content and a focus around long-term thinking to that content to you. So hopefully, if you are a member, you have already seen it, and we're working on bringing that to an even broader audience as we go. As many of you know, before these talks, we usually start them with a short film about long-term thinking. And this one was actually found for us by our videographer, Chris Baldwin. And I think you'll see that it brings a new vantage point to something that you've seen before, but also then pushes that through time. Enjoy.
Not your average redwood burl coffee table. So 10,000 year time frame. 10,000 years back, 10,000 years forward, seems like a long time. And we find that we keep finding or getting the kind of framing that we want from astronomical time. Things that happen at planetary pace, cometary pace, eclipse pace. And last month, Carolyn Porco was here talking about life nearby in the solar system, assuming that the sun, is not itself alive, which hasn't been determined one way or the other yet. There's a book called Star Maker by Olaf Stapleton, which raises interesting questions. She was focused on Enceladus, one of the moons of Saturn that makes plumes coming out of what looks like underwater ocean that, who knows, she was hoping we could put a lander there and it might be raining microbes, which might be our kind of life or a different kind of life. Pretty primitive. Not entirely a certainty yet. So is there any place in the solar system that we know has life, and what's going on with it? Ask an astrobiologist. Our speaker, David Grinspoon.
All right, thank you so much. It's really a pleasure to be here. Thank you all for coming out this evening. Among many other things, it's always great to be back in San Francisco. I actually lived here many years ago when I was a postdoc down at NASA Ames, and I always avail myself of any excuse to come back, so thank you. The approach that I am taking to our existence here, to humanity on Earth, comes from my field of astrobiology. And you may think that's a little weird because astrobiologists think about life elsewhere, right? That's true, but it also, I think, gives us a perspective on our home planet. The specific project that I'm going to expound upon a little bit this evening, it came to me as an opportunity because I saw this ad a few years ago for a new job position that had been created at the Library of Congress called the Chair of Astrobiology. And they were looking specifically for somebody to undertake research at the intersection between astrobiology and the humanities. And I saw that ad and I thought, wow, maybe this could be the opportunity to write that book that I've been wanting to write for the last decade, but haven't been able to fit into my career as a mid-career scientist. You get too busy to do really interesting things. But anyway, so I applied, and I was very gratified to be selected as the inaugural chair of astrobiology at the Library of Congress, and my project was this. The title of my proposal was Astrobiology and the Anthropocene Era, exploring the potential roles of life and intelligence on Earth and beyond. So you've heard this term, the Anthropocene, or the Anthropocene, as our British colleagues say, or the Anthropocene. There's many debates about it, including how do you pronounce the darn thing. But the idea is that we've entered a new geological stage defined by this new force changing the planet, humanity. It's a contentious idea because on one hand it seems very self-aggrandizing and egotistical. Why should we name a geological age after ourselves? On the other hand, you could look at it as an acknowledgement of responsibility. If we just look at the numbers of how the carbon cycle, the hydrological cycle, the climate, the land surface, all of these physical aspects of our planet are being changed rapidly by this new force, and that's us. So I think that, to me, the concept has a lot of merit, and I thought, as someone who studies planetary change, having mostly focused on other planets, wouldn't it be interesting to apply that perspective and those same techniques to look at this transition that's happening on Earth now through the lens of astrobiology? So that was that project, and it led several years later to this book that came out earlier this year, Earth in Human Hands. And this evening I'd like to share with you a few of the ideas that wound up in that book as a result of that project. So, got to get the hang of this clicker thing. Here is the history of the universe on one page. The compression ratio is rather large. You have to leave out a few of the details. But the story of cosmic evolution, this is our attempt to tell the story of the universe with a focus specifically on the major transitions that matter and energy have gone through from the moment of the Big Bang in the upper left to what we so proudly call civilization on the lower right, with the question marks and the arrow suggesting that there's no reason to think that this is the end of the story. This is a stage in the story. This is also being called big history now by historians. It's basically the same thing. Astronomers call it cosmic evolution, and they do a really good job with the beginning of the story and a lousy job with the end of the story, whereas the historians call it big history, and they do a great job with the end of the story and a lousy job with the beginning of the story. But we're basically all telling the same story. And so it goes from, starting in the upper left, the Big Bang, and that makes galaxies and atoms, which which form into galaxies, and then within galaxies you have molecular clouds that collapse into stars. And if you look at the sort of magnifying glass, that's what's happening on the micro scale, where you've got elements and they form into simple organic molecules and then complex organic molecules. And around some stars, planets form, and on the surface of at least one planet that we know of, that chemistry did something really interesting, became self-replicating, which led to the possibility of Darwinian evolution, and you had life. And then on at least one planet, it kept going to some interesting phenomena we call complex life. And part of what we're trying to do, the overall project, if you will, of astrobiology, is to understand how universal these later stages may be. We've learned through the techniques of astronomy, astrophysics, that those earlier stages, everything on the left side of that page, really is universal. Everywhere in the universe there's galaxies, there's stars. And then one of the big intellectual revolutions of our time, the exoplanet revolution, has allowed us to learn that this next stage, the top right, the formation of planets, is in fact also universal. We didn't know that back when I was a postdoc here at NASA Ames in the early 1990s. This is recent and profound knowledge that now we know that every star in the sky, when you look up at a night sky, basically every star has planets. So that phenomena of planet formation has moved from this speculative column of, well, we think it ought to be universal because this location seems normal, why shouldn't there be planets everywhere, has moved from that column to the verified, we know it's universal. And if anything, with astrobiology, we're trying to do that with these later stages. Can we move them from the column where biology is now? Well, it seems like it should be universal. There's nothing we know of here that seems so unique that shouldn't be happening lots of places, but we haven't yet found the evidence. So that's sort of the overall point of astrobiology. Now we come to our own planet, and let's look at it just for a second, if we can, from the perspective of an alien astrobiologist. Imagine that you were some very patient alien species with a long attention span watching our planet for, say, the last few 100 million or the last few billion years. And what would you have noticed? You would have certainly seen a lot changing on the planet over that time. The sort of morphing jigsaw puzzle of the continents drifting around, coalescing and breaking apart with continental drift, the rhythmic pulsing of the climates, the ice ages, the polar caps shrinking and expanding over many tens of thousands of years. But over all that time, the night side would have just been pretty much an unbroken black. Maybe there'd be occasional lightning flash, splash of aurora. And then about 400 million years ago, when the continents became forested, you would have seen the occasional forest fire. But other than that, the night side would have been an unbroken black all those billions of years, until just very recently, boom, what's this? There's definitely something new and something very strange going on this planet. So how can we characterize that? The one way we think about deep time, of course, you've seen this, is the geological time scale. This is a cartoon form of it. And over on the right side, these epochs, these are one of the smaller ways that we break up time. And the Anthropocene has been proposed as a new epoch to follow the Holocene, which we've been in more or less since the last ice age. And it's okay if you can't read all the fine print on the right there. In a way, that's sort of the point, that those epochs come and go. They're not, from the Earth's point of view, they're not that big a deal. They represent fluctuations in sea level, minor extinction events, change in climate, but really epochs come and go all the time. But as you go over to the left side of that chart, you get into larger and larger demarcations of time. And all the way over on the left, you see the eons. The eons are the really profound transitions in Earth history, are the eon boundaries. There have only been 4 of them so far. One thing I propose in my book, and I'll come back to this a little bit later, is that we may be seeing not just a epoch boundary with the Anthropocene, but something much more profound, the beginning of a new eon. Now, why would I say that? These eons represent major transitions in Earth history, where before and after Earth was a completely different planet. And each one of them is a transition in the relationship between life and the planet. So, for instance, the Hadean on the bottom there, that literally means hellish. And you would not have wanted to be alive on the planet then. There was no life because it was all asteroid impacts and volcanoes and steam and magma. And then the Archean, at 4 billion years ago, is more or less, that boundary is more or less the origin of life. And the planetary environment had sort of stabilized and calmed down to the point where you could have continuous life. And then, and by the way, I'm really simplifying, so if there's any geologists in the audience, don't pelt me with objects, please. But the boundary between the Archean and the Proterozoic at 2.5 billion years ago, I think of that as when life took over the planet chemically. It's closely associated with what we call the Great Oxygenation event, or sometimes called the oxygen catastrophe. I'll get back to that as well. When life filled up the atmosphere with oxygen to the point where it was actually a poison and wiped out a lot of other life. But that was when life sort of chemically took over the planet and deeply impregnated itself into the chemical and physical workings of the planet. Moving on to the Proterozoic, Phanerozoic boundary, that's the origin of animal and plant life, when life got big and complex and multicellular. And then that's supposedly it. The Phanerozoic is where we are. Although I propose, and I'll come back to this, that potentially we're at an eon boundary now with an equally profound transition in the relationship between life and the planet. The moment where cognitive processes become planetary processes. There have been many forms of life that have changed the planet, but there has never before been a geological force aware of its own existence. And to me, that's a very profound change. I'll come back to that thought. The other thing I wanted to say is that as an astrobiologist, these eon boundaries are interesting because we're interested in the universals of planetary evolution and biological evolution. And all these little demarcations on the right of epochs and periods, they're not going to match up with what we find on other planets. There's not going to be a Jurassic on another planet or a Holocene because evolution is too random. They're not going to be dinosaurs and people on other planets. There may be organisms with some of the characteristics that play some of those functions. But these eon boundaries on the left, as an astrobiologist, I could imagine looking for those on other planets. An origin of life, even an oxygenation event, because photosynthesis is such an obvious innovation. I do expect to find it on other planets. Multicellular life, and this question of the Sapiozoic, could you have cognitive life become part of planetary functioning? To me, these are all transitions that are of astrobiological significance, potentially, that you could potentially find and map into the story of other planets. So, the local story here began about 4.5 billion years ago with the origin of the planets in our solar system through a process that we call accretion. Basically, when the sun was born, it was surrounded by a disk of gas and dust that was congealing and coalescing as it cooled. It was radiating energy into space and cooling, which caused it to snow, not just water ice snow, but little snowballs of rock and metal and different kinds of ices, depending on how far it was from the sun. And then those snowballs sort of started to congeal and collide and coalesce into larger pieces, and the collisions became more and more violent. and the chunks became larger and started to gravitationally yank each other around. And at the end of that process of accretion, there were a few survivors, and that was the beginning of the planets as we know them today. And then a lot happened. I'm going to fast forward and skip a few crucial steps. But here we see ourselves on this one planet where, as I mentioned earlier, it suddenly lit up. And if you were this alien watching this planet, this switching on of the nighttime lights would correlate with all these other changes in the atmosphere, changes in the land surface, and even very recently, in just the last 60, 70 years, just a blink of an eye in the life of the planet, another very strange kind of behavior started, which is that little bits of that planet started springing back up into space, from whence at one time it all fell down. This is what I call the curious anti-accretion. Curious in two senses. It's a weird thing for a planet to do, suddenly have bits of itself start flying back into space and buzzing around and zooming off to the other planets. But also the hallmark of the advent, the arrival of a certain kind of curiosity here on Earth, technologically enabled curiosity, going out to the other planets, seeing what's there, radioing home the information that these little robot emissaries find, and of course surrounding our own planet with this mycelium of detectors and communicating transmitters. Our planet started to self-observe and to observe the neighbors and go out in search of answers, in search of its own history. And largely that's what I've been involved in for my career as a planetary scientist, is modeling the histories of other planets, and I've been fortunate to be part of a few teams of people that have proposed and built and flown spacecraft to other planets to learn things about climate history and catastrophic change on planets. That's sort of my day job. And one thing we've learned through this exercise of comparative planetology is that the rocky planets, Earth and Venus and Mars, and now we're starting to learn a little bit about the rocky planets, just beginning to really ask questions about the rocky planets around other stars, but they seem to have similar origins in early environments. What we've learned about early Venus and early Mars tell us that rocky planets seem to start out with warm oceans and organic molecules, and the kinds of environments and physical requirements that we understand are necessary for the origin of life. So it may be that the conditions for the origin of life are not all that rare on Earth-like planets. And what seems to be more rare is the persistence of life, that maintaining those conditions over billions of years. For whatever reason, and we're still in search of that reason, something happened on Earth that apparently didn't happen on Mars and Venus, the formation of a robust and self-sustaining biosphere. And we've learned that life, the influence of life goes very deep on Earth. You've heard of the Gaia hypothesis. It's not just the atmosphere, but now it turns out the physical properties of the Earth itself, even the interior of the Earth. Earth is a planet that's thoroughly modified by life. And in fact, I like this quote by my colleague Colin Goldblatt at the University of Victoria in British Columbia. He said, "The defining characteristic of Earth is planetary scale life. And Earth teaches us that habitability and inhabitants are inseparable." In other words, when we go out looking for habitable planets elsewhere, we can't just look for physical conditions that would be nice for life. We have to look for a biosphere, in effect, a living world. Like we have here on Earth. So it seems as though early on in its existence, Earth went through some kind of a juncture, went down a different path. Maybe took the road less traveled, I don't know. But which differentiated itself. And life, we didn't just have an origin of life, we had a sort of takeover of the Earth by life. And now we find ourselves at a new kind of planetary juncture, more recently, Earth has come under the influence of a new type of geological force, the global activities of humanity, defining this Anthropocene epoch. And the question that I am sort of obsessed by, I guess, thinking of it in this context of overall planetary evolution, is this: could intelligence, like life, become a planetary property? You know, life is something that we had an origin of life on Earth, and then life became a robust, self-sustaining property of the Earth. Now we've had arguably an origin of intelligence on Earth, although I think that's debatable. But the question is, or one question is, when we think about longevity and persistence, can this become a planetary property? Can the fact that cognitive processes are now affecting the evolution of the planet, can that become some kind of a self-sustaining and robust property of the planet? Now, going back in planetary history a little bit, I mentioned this briefly, but we are not the first species to come along and radically change the planet. You could even say that we're not the first species to come along and, in the quest for a new energy source, exploiting that energy source, polluting the atmosphere profoundly to the point where mass extinction and climate catastrophe ensued. That's been done before. You know, nothing's it's so hard to be original these days. Every idea's been had. But so these little guys, the Cyanobacteria, they look innocent enough, don't they? But a couple billion years ago, 2.5 billion years ago, they discovered this new energy source, solar energy, and started to do photosynthesis very efficiently, whereby they're breaking up water and CO2 and spitting out the oxygen and making organic stuff for metabolism. And that oxygen is a highly toxic gas to organic matter. Oxygen reacts violently with organic matter. And this was, when it started to build up in the atmosphere, that was poison and led to extinction of a lot of species. All the species that couldn't sort of hide in the mud or in what we call an anaerobic environment were wiped out. Now, of course, that sounds weird to us because we love oxygen. I know I do. Good stuff. But that's because we've evolved the capacity to take advantage of those violent reactions between oxygen and organic matter. In every cell of your body, there are these little power plants that metabolize, that do a sort of controlled burn of organics with that oxygen and store up the energy in these phosphate bonds, and that's how we live. So before we evolved that capacity, this was catastrophic. Not only that, but it probably led to the greatest climate catastrophe the Earth has ever known. There's something called the Paleoproterozoic snowball Earth, where Earth was completely covered in ice and could have almost led to the extinction of life on Earth. And we think that happened as a result of this pulse of oxygen wiping out the methane that at that time was supporting the greenhouse on Earth and caused a climate crash. So, not to belabor this, but we're not the first species to come along and sort of wreck the planet. But obviously there's something different going on now. What is that? It's another way of getting at this question of what kind of a planetary phenomenon are we? So we're not the first species to cause global change, but clearly we're not bacteria. You know, we have some sense of responsibility. So what exactly have we got the cyanobacteria didn't? And you know, a lot of people have attempted to address this question of human uniqueness, and we talk about things like language and tool use and art and technology. And, you know, there's a long history of, you know, a lot of these you can find exceptions. But collectively, I think we can agree that these kinds of human qualities, including the sharing of cumulative knowledge over generations. There's clearly something new going on here, and without trying to put a name on it, I'm just going to refer collectively to the set of human qualities. But this one on the lower right here responsibility is key. That's what differentiates us, of course, is that we can see what we're doing, we can see what's coming, and we ought to have some sense of responsibility. But in order to get at this question in a slightly different way of really what's different about this transition, I've looked at all the major kinds of catastrophic changes that can happen to planets like ours. And I've put together a sort of taxonomy of planetary catastrophes. And I've decided that with respect to the influence of life, oh yeah, forgot about this slide. So we can ask cumulatively, are these qualities adaptive or an evolutionary dead end? You know, we're very proud of our abilities, but we're not completely convinced that this experiment's going to work here, right? So we can ask, is this an evolutionary dead end or some kind of potential gateway to great longevity? If civilization is now a planetary process, what are its prospects here and elsewhere in the universe? So one way to look at this, I've put together this sort of taxonomy of types of planetary change categorized with respect to the role of life. So what I call planetary changes of the first kind are random catastrophes. These are dramatic planetary changes where life has nothing to do with it. You know, you're just in the wrong place at the wrong time. An asteroid hits is the canonical example. But there are other examples too. Several mass extinctions have happened because of these dramatic changes in the interior convective activity of the Earth, which lead to this massive belch of volcanic activity, which causes climate change and a mass extinction. So these are the changes where life is just an innocent bystander. You know, this is when bad things happen to good planets. Planetary changes of the first kind. Planetary changes of the second kind are what I call biological catastrophes. And I symbolize that here with the green leaf, because I already mentioned the cyanobacteria and what happened when life figured out photosynthesis. These are catastrophes that happen when life is just doing what life does and opportunistically evolving, finding new ways to survive, multiplying, and in the process, changing the environment, often to the detriment of other species, and sometimes leading to a planetary catastrophe. So there are a few other examples of this, but the most dramatic example is the Great Oxygenation Catastrophe. Now, the next two kinds of planetary change, this is where the cognitive processes enter into it. But I want to emphasize that there are two different ways that this can manifest. What I call planetary changes of the third kind are inadvertent planetary catastrophes. And I symbolize this here with traffic. This is when a species develops technology, begins to extend its reach, and is very clever at applying this to solving local survival problems. So clever, in fact, that they multiply and spread around their planet. And having no idea they are doing so, begin to cause planetary scale changes. And this leads to what I call the Anthropocene dilemma. I'm getting overzealous with my clicking, and there we go. This leads to what I call the Anthropocene dilemma, which is when you have global influence, but not any sense of global control. And it's cognitively, it's on the level of a child who has not yet developed situational awareness. So you're not aware of the effects that you're having. You walk into a room and you smash things over, and it's the bull in the china shop, and it's unstable, it's dangerous. So, and it's symbolized by traffic here, because you look at this picture, and each one of these cars is being driven by a person with agency, and they can do a fine job of seeing obstacles coming and steering around them, hitting the brake when they need to, works just fine. But if you look at the system as a whole, you can ask, well, who's driving the global transportation system? And the answer is kind of Well, nobody. So we're participating in it, but we're not controlling it. And when we talk about a lot of global processes, we talk about the market, or we talk about the other phenomena that we participate in but not necessarily fully control. It's often as though we're describing something external to ourselves, and yet we participate in it. So this is what I mean by the inadvertent kind of planetary change. And examples of this, the obvious example on the left here is the Keeling curve that you know about, the dramatic rise in carbon dioxide through industrial activity. And this slide is a little bit outdated. It says 395 ppm. Now it's over 400. You have to keep updating this slide when you give talks about this. And all of the phenomena this results in, and I don't need to, for this audience, talk at length about this. Obviously, the change in CO2, and this is this marvelous animation I got from the Cal Academy showing the sources and sinks of CO2 over a year, and there's actually a lot there that you can see the CO2 sort of emerging from the dense industrial areas and actually being taken up by the forested areas, so it's pretty cool. And over on the right, the sort of frightening decline of the sea ice. And this is the most concerning, but not the only, of these inadvertent kinds of changes that are going on now. This is, of course, the famous ozone hole, which is also something you know about. And you can see, starting in the 1970s, we discovered this. And by the way, we discovered this in part because we were exploring the planet Venus. And some of my colleagues were trying to figure out a puzzle in the upper atmosphere of Venus, why there was not enough oxygen. Venus is mostly CO2, so it's a great example of the greenhouse effect gone wild. And there's a question of, in the upper atmosphere, there should be a lot of oxygen because CO2 is being broken up by ultraviolet light, but the oxygen molecules are missing. So people were trying to solve this, and some scientists said, well, there's these experiments I saw in this lab over here that shows that chlorine destroys oxygen compounds, in the right situation. I wonder if that could be going on. And they did some more observations and found chlorine and said, oh, aha. And then some other scientists read that paper and said, oh, well, what about all this chlorine we're putting up in Earth's stratosphere with these new miracle-safe refrigerants, CFCs? And they saw that and they went, oh, wait a minute, and sort of put two and two together and sounded the alarm. And then you can see the ozone hole deepens here through the 1980s, but then it starts to level off because even though this is definitely a classic example of an inadvertent global catastrophe, which unchecked could have truly been catastrophic, it's also my first example of what I call the fourth kind of planetary change, which is intentional change, because the story of the ozone is that when the scientists sounded the alarm, there was a global discussion, one might say heated global argument about what to do about it, and there was denial. There was professionally supported denial, where experts were hired by the companies that manufactured these things to muddy the waters and put out what we might today call fake science, disputing this. A lot of the dynamics we see in play now with our problems with fossil fuels and climate played out, but what happened in this case was that global agreements were made. Actually, what happened was the ozone hole started opening up over Antarctica, and that scared people. It even scared the directors of the DuPont Corporation. And they decided, okay, let's do something about this. Global agreements were made, treaties were signed, there was the Montreal Protocol for the regulation of ozone destroying substances, or whatever it's called. And it wasn't just that the companies suddenly became fully altruistic. They also saw there was money to be made in making the replacement refrigerants that would be necessary, and they ran out and got the patents for those. But however it played out, it's a success story in that we saw this problem coming and we worked out a global solution, and the ozone hole is now on track to being fixed. It's not fully fixed yet because it takes about 50 years for these chemical reactions to reconstitute the ozone, but it's definitely I think, an important example, a proof of concept that there is another way, that we are capable of another way of responding to a self-induced planetary emergency. Now, moving on to other examples of this fourth kind of planetary change, intentional change. Obviously, our most urgent need now is to transform our energy sources into ones that are not wrecking the natural systems that we and the creatures we share this planet with depend upon to survive, and that's symbolized in the upper right here. And that is a transition that is in progress. And we're all, I think, those of us paying attention, are frustrated by the pace of that transition, but it is occurring. There's no doubt in my mind, 100 years from now, we will not have a fossil fuel-based economy. We will get from here to there. It's a question of the pace and how much damage we'll do along the way. I believe 100 years from now, we'll be repairing some of that damage. But at any rate, as far as intentional changes to the planet, that is obviously our most urgent challenge, but it doesn't end there. When we think farther into the future and we start to conceive of ourselves in this role of possibly intervening in the planet, then we start to realize other responsibilities. And I describe them as responsibilities because once there's an intervention that we realize we could take that would save many, many species, would possibly prevent a mass extinction, then we sort of become obligated to attempt to make that intervention. So looking at the rest of this slide here, I've got on the bottom left, I've got the possibility of dangerous asteroid impacts, and on the bottom right, I've got the possibility of future dangerous, quote, natural climate changes, which left to their own devices would, on a longer time scale, lead to some very dangerous behavior on this planet. Let me expound upon that just a little bit. This is actually data. Each one of these little insect-like objects in this swarm, each one of these is a known Earth-crossing asteroid. These are all objects that could hit the Earth in the future. Now, this is really sped up, so don't lose sleep over this. If there's something you want to lose sleep over, I can give you another suggestion. But the point is that this is a very real, almost actually inevitable threat if you go out on a long enough time scale that there will be asteroids that can hit the planet. But the good news is we actually know how to do something about this. It's a tractable problem. Given enough time, and chances are we would have a lot of time, because what we're doing now is observing these objects, and if we had a decade or 100 years, which we probably would, to see something coming, it's not that hard to go out and give something a little nudge. So knowing about this, then I think it sort of becomes our obligation to develop that capability. And I actually think this is what I call the big payback. I think in the long run, it's quite possible that we could prevent a lot more extinction than we're causing now. We could prevent the next mass extinction. And I mentioned intentional climate change. We think of climate as something, we often think of climate as something that left to its own devices is friendly and benign, and if we would just be hands-off and let the Earth as a paradise left to itself, it will take care. That, of course, is an illusion. An illusion because we've come along at an unusual time of Earth history. Our civilization, if you can call it that, has sprung up in this 10,000-year period of relatively warm and stable climate. But of course, you go out to tens of thousands of years, and that's no longer true. There's this Milankovitch cycle, the Ice Age cycle, and we do not want to try to live through another ice age. Our civilization would not survive that. North America was covered with a mile-thick sheet of ice in the last ice age. But it wouldn't be that hard to prevent if we're around 10,000, 50,000 years from now. I think we'll easily know enough to prevent that. But we have to be comfortable in that role of thinking ourselves as not trying to just sort of avoid messing up the Earth. That's our first task, is to get over this phase of sort of climate vandalism that we're adolescent climate vandalism that we're perpetrating right now, but it doesn't end there. The more mature phase is realizing that we have the possibility of intervening on behalf of life in the longer run. So if you want to get nerdy about it, we can sum up some of these planetary changes of the fourth kind in terms of different time scales. And on the y-axis here, I have sort of where we are. The very top are global problems that we've solved, and I have the smallpox vaccine as an example of there. And the ozone is a problem that we're at least on track, and that's, both of those are, I put in this is log year, so those are like 100-year time scales. On about a 1,000-year time scale, we really have to be serious about planetary defense. I got Mars terraforming in there. It's something we could talk about if you want. I put it in there because it's another example of intentional intervention in planetary evolution as opposed to sort of inadvertent or random. When you get up to about 100,000 year time scales, then you really have to worry about ice ages and whether we want to intervene in them. And then if you go all the way to the right-hand side here, eventually, if there's anybody still here, we or our descendants or our creations, or the descendants of our creations, or somebody else completely who came along, the point is somebody's going to have to deal with the fact that the sun is actually not a fully renewable energy source. If you go to billion-year time scales, the sun will run out of fuel and consume the Earth. But I maintain if anybody's around for that long, then that will also be a tractable problem, probably because they'll just be able to move. But so coming back to Earth for a second, the Anthropocene, there's a lot of talk and debate about one of the things people love to debate is when it started. I'm not that interested in that debate. I mean, they're all interesting ideas. Is it the nuclear bomb, isotope horizon? Is it when the Industrial Revolution, the steam engine, and we started putting CO2 in the atmosphere? Some people say it was 8,000 years ago when we started large-scale agriculture and changed the land and the climate. It doesn't really matter to me when we say it started. The more interesting question to me is, when will it end? Or will it end? Or what really is it in Earth history? Is it an event like the Cretaceous-Tertiary boundary, where when the asteroid hit, there's a centimeter-thick layer of clay all around the Earth where the detritus from that asteroid hit? That's an event in Earth history. Or is it something more sustained, like it's often called an epoch? Epochs tend to last 10 million years or so, 15 million years. Or is it actually something different, a planetary transition, like the origin of life or the Cambrian explosion? As I mentioned at the beginning, our planet has been through a few of these transitions where it was a completely different planet before and after. And in my view, that's what we have to shoot for. We have to imagine that now that we're here and we realize we can play a role on this planet, we have to choose a constructive role rather than a destructive role. And part of that choosing a constructive role is in imagining ourselves on a long time scale and thinking, what would it be, what would it mean for this cognitive process to actually become a sustained part of planetary functioning? Now, when we get to these thoughts of very long time scales, we often intersect with some of the ways that people are thinking in the field of SETI, the search for extraterrestrial intelligence. If you look at the literature of SETI, even going back to the 1960s when people first started seriously, Frank Drake and his colleagues started seriously listening and thinking about what it would take to make contact with extraterrestrials, the people doing the theory of SETI quickly realized that the crucial question was all about longevity of civilizations. You can do the math. You've probably seen the Drake equation with all these different parameters for how many planets there are, what fraction of them have life, what fraction of them this, that. But the crucial thing is, how long do civilizations last? If civilizations all do themselves in within 100 or 1,000 years, then you can do the math and show there's going to be nobody you can talk to. Because the average distance to the, not that there's nobody there, but the average distance to the nearest civilization will be so long that the chance of you and them being alive at the same time and able to communicate is basically zero. On the other hand, if civilizations, even a small fraction of them, can last a long time, say thousands, tens of thousands, hundreds of thousands, millions of years, even longer, then it's quite likely that there would be one nearby enough to communicate with. So it's all about longevity. And when I think about this question of this transition that Earth is undergoing now, and try to abstract it, so it's not just about humanity and what we're doing here, but a kind of thing that can happen to a planet where life evolves to a point where cognitive processes start to become planetary processes. And I wonder if that might be happening elsewhere in the cosmos. It's just another way to sort of abstract what's going on here. And then I realized that the central problem of SETI is really the same as the central problem that we are facing now as a civilization, as a species on Earth, which is it possible to develop a mature, long-term, healthy relationship with world-changing technology? I think it is. And I don't want to go on at length about why that is, because I want to kind of wrap up here so we can get to the discussion part. But let me just make a couple of points. It's very clear to me that in order for our civilization to survive, we do need to become a new kind of entity on this planet and learn to live comfortably over the long haul with world-changing technology. And this is something that in my book, I call this Terra Sapiens, the need to become Terra Sapiens, which of course sapiens means wise. And when Linnaeus named us, he was looking for a phrase that would differentiate us from the other hominid species, and he called us Homo sapiens, wise apes. Maybe that was a little bit of overreach or wishful thinking. And yet I find it useful as an aspirational name for this epoch that we may be developing. Now, people say that's impossible. They say, look at our behavior on Earth now. How could you even imagine we can do that? But I say, let's look at our deep history, not just our history of the last few decades or hundreds or even thousands of years, but our history as a species. And one thing you learn when you look at our deep history of species, the deep history of our species, is that we are unique in our capacity for self-reinvention. And in times of existential threat, we have completely reinvented ourselves before. And often, it's interesting, if you look at the history of our ancestors in Africa, pre-humans in Africa, it's often in response to climate change that we've invented and refined new capacities for survival. This map here on the left, this is a place called Pinnacle Point near the southern tip of Africa. And it's the place where a lot of anthropologists now think that the origin of modern humans may have taken place. There's an archaeological site there where it seems as though these were the survivors when the human race, or the pre-humans, almost went extinct. About 190,000 years ago, there was a genetic bottleneck, and we were almost completely wiped out, down to probably fewer than 1,000 individuals. And this may be where we made our stand, Pinnacle Point. And we had to learn a completely different way of surviving, because up to that point we were hunter-gatherers. But there was an ice age in Africa at that time, and we couldn't hunt the way we were used to because the game died out because of climate change. There was nothing to hunt. And the people at Pinnacle Point found ways to hunt for shellfish, and they invented new technologies. And this is the origin of what is called long-chain complex recipe technology. And what that means is these are technologies where you have to go through some complex set of steps to produce something like smelting of metals or heat treatment of rocks, so that the product that you're getting is not obvious from the ingredients you start with. The steps are it's long chain complex recipe technology. And it requires new levels of language and cooperation, and you have to be able to teach it to the next generation. And there's art here and evidence of pigments and personal adornment. So this may be where we became human. It may not be, but the point is there are many examples like this where faced with catastrophe, we reinvented ourselves in ways that required cooperation and invention on larger scales. And that's what we humans are good at. And when people tell me there's no way we're going to harness ourselves and create this society where we actually are able to use our technology as mostly as a survival tool rather than to threaten ourselves, I ask them, imagine trying to describe a modern city to the people of Pinnacle Point and the way we live now. It would be very hard to do. And maybe that's just as hard as it is for us to imagine Terra Sapiens, the reinvention that we are perhaps beginning now. So when I talk about the Sapiezoic eon, obviously it's aspirational. The thing is, in order for a period of time, a geological period of geological time to be an eon, it has to persist not just for thousands, not just for millions of years, but for billions of years. So we can't possibly know if it's an eon. We won't know it for millions of years. And yet, to me, that's the way to think of this, is that we're in it for the long haul. Like it or not, we are now planetary players. I don't believe we have the option to stop being a geological force, so we need to learn how to be a good one, how to be a constructive one. And one last point. The metaphors we use to describe ourselves are so often negative and destructive. We're a cancer on this earth. We're criminals. We're raping the rainforest. Now, I understand the origin of those metaphors. You look at a lot of our behavior, and it's reprehensible. You know, human development does tend to have a cancer-like property when seen from the air. And, you know, when I hear about the white rhinos of Africa going extinct at our hand, you know, it's unforgivable. It is a crime. And yet, there's something different here, because a cancer doesn't stop and have a conversation with other cancer cells and go, hey, you know, maybe we shouldn't be a cancer, because if this person dies, then we're going to die too, you know? So there are, my point is that these metaphors describe a certain component of our past, but they don't have to describe our future. I think we can find other metaphors. There's the metaphor of youth, of just waking up to find out what we are here on this world. There's the metaphor of the unschooled driver, where we're driving down the road and we suddenly realize, oh, I'm driving this big rig and everybody I love and everything I care about is in the back, but I don't actually know how to drive. I better learn in a hurry. To me, that's our situation on Earth. Or there's on the right here, there's the metaphor of the sleepwalker, you know, of sort of waking up to find ourselves in the middle of committing these crimes and saying, oh, wow, what are we doing here? And then finally, maybe you're familiar with the trope of science fiction, the generation ship story, the most famous of which is Orphans of the Sky by Robert Heinlein. This comes from the idea that if people are ever going to travel between the stars to other star systems, the distances are too far, using any technology we can imagine, for people to go within a human lifetime. So how do we get to the stars? One way is to build these generation ships, where the people who arrive are the descendants, multiple generations later, of the people who set out. And there's a lot of good stories about this. And in those stories, something always goes wrong. You know, there's been a mutiny or a revolution or some kind of breakdown, and the people on that ship don't realize they're on a generation ship anymore. They think this is just the world. And then our protagonists, our heroes, they figure it out. And they go, oh, wow. And, you know, they find a porthole and they look out and they see the stars, or they find the control room and they go, wow, we're on a ship. We're going somewhere. We have to wake everybody up and tell them to, you know, what's going on, see our reality. And to me, that's sort of where we are on this planet right now. is that, we are realizing the nature of our existence on this planet, and we just kind of have to wake everybody up so that we can do a better job of driving this thing. You've probably seen this. I want to end with this lovely cartoon by R. Crumb, and from a local publication of some ill repute. And this is, Mr. Crumb very generously gave me permission to use his artwork in my book, which I was very pleased by. And this is his brief history of America. And you can see it starts off with this pastoral scene in the upper left, and it's the same scene every decade. And very slowly, the influence of modern, technological society creeps in, and it's still quite pastoral for the first few frames. Then, of course, by the bottom right, we've, even though every step is gradual, we've come to this rather completely urbanized landscape where there's no trees, and the sky's got a sort of unhealthy pallor. And then I don't think you can see it, but on the very bottom right, there's this little thing. He says, "What's next?" And that's where it ends. He did this in 1979, but sometime, I think about a decade later, he was asked if he would do a sequel, an epilogue, and he did 3 more panels showing the future. 3 possible futures. The top one is worst case scenario, ecological disaster. Not too much to be said about that, other than that's what we want to avoid. But then the bottom 2 are very different. The middle one says, the fun future. Techno-fix on the march, and there's people in flying cars, and everything's all sort of regimented, but very nice. And there are trees, but they're planted in nice, controlled rows. And then the bottom one is the ecotopian solution. And, you can see people are living in tree houses and playing acoustic instruments and riding bicycles. And these 2 bottom frames, to me, symbolize in a sort of cartoon way this debate that's going on now about our future between the eco-pragmatists and the traditional sort of reactionary conservationists. And, in a cartoon sense, the eco-pragmatists want this techno-fix on the march, and the traditional conservationists want the ecotopian solution. And in my view, they're sort of both right, that the future's going to need some combination. We need innovation, which is really this middle panel, and we also need restraint, which is this lower panel. But I think some wise combination of these 2 bottom philosophies will lead us into the 22nd, 23rd century in a way that will avoid the ecological disaster scenario. So that's it. I want to end with a quote from one of my heroes, Dr. Martin Luther King Jr. If we are to have peace on Earth, which I interpret also to mean if we're to build a sustainable global civilization, then our loyalties must transcend our differences, and we must develop a world perspective. And on that, I will stop. So thank you very much.
Have I lost? Now I've got sound. And now I'll probably destroy it. I'm going to show you a photograph. First, I'll show it to everybody else. It's a photograph that I took in July 1976, and it's at JPL, Jet Propulsion Laboratory in Pasadena. And we're looking at coming down on a computer screen what was the very first images from the Viking lander. And I'll ask if you recognize the character with the glasses who's looking at it.
I absolutely do. That's Uncle Carl. Yeah. Carl Sagan. Those Viking landings were seminal events in my teenage life. And that's Uncle Carl looking at one of the first scenes from the Viking 1 lander on Mars, which is our first lander. Yeah, amazing.
Later in that day, you saw these images building, and it's interesting because they came in really mucky. And then the computer algorithms cut in and started to make sense of the grays and the whites and the blacks.
Made them look
so that
nice.
you could see that you were looking at the foot of the lander and Martian landscape behind it. And of course, Carl was there, and Ray Bradbury was there, and Heinlein was there, various people there. I was there because Governor Brown was there, and I was part of his entourage. And Carl, of course, was set up with a mock setup of the lander, and various television networks are over there, of course, talking to Carl Sagan. So, Carl, what do you think? Is there life on Mars? And he says, big grin, there is now.
I love it. Yeah, I remember that day. It made a big impression on me.
Yeah, what's your relation with Carl over the years?
Well, it's funny. I did grow up calling him Uncle Carl because he and my dad were best friends when I was a kid, and he was a big inspiration. They were both Harvard professors at that time. That was before Carl got kicked out of Harvard for political activities and ended up at Cornell.
I didn't know that happened.
Well, he was denied tenure, and there's no official reason, but he was the faculty advisor for the SDS. And there's a lot of speculation that was why. But at any rate, so I grew up with him around the house a lot, and telling bedtime stories and stuff, and showing up with pictures of planets, and very, very inspirational figure in my life. And then later on, we ended up collaborating on some scientific studies of climate on early Earth. So sort of went full cycle in that way.
And also you're out giving popular talks with a funny hat. And, at the time, I remember a lot of scientists basically peeing all over Carl Sagan for being so popular and so engaged with the
Yes.
public, and billions and billions and all of this stuff. And it was easy to mock, but he did a lot of serious science. He did some serious art, like with the book Contact, which became a good movie, Contact. And I think he set in motion for your generation a sense of responsibility to be more transparent, more communicative about the science that one is doing. Is that your sense?
Absolutely. Yeah. No, I mean, Carl got a lot of crap from the scientific community, and a lot of it was because people said he was just a popularizer. Like, that was like something wrong to be speaking to the masses. It's like Galileo got in trouble for writing in Italian, right, rather than Latin. There's a long tradition of people getting in trouble for using the people's language. But he was given a fair amount of crap, and some people thought it was jealousy, and maybe it was because he was the one on Johnny Carson, but it was not seen as a fully respectable thing for scientists to do. But now I think people realize, as you say, much more that it's the obligation and, in fact, a pleasure of being a scientist is to go out and communicate with people. What's the point of doing it if you can't talk about it, especially since it's mostly public funded? So he was a trailblazer in that way. He also didn't shy away from controversy with nuclear winter, and he got into some territory that pissed off the powers that be a little bit as well. So that was probably part of it. He didn't always choose the easy path.
Two questions about ice ages. Jim Lutz says, shouldn't we invoke a small ice age to avoid sea level rise problems? It's one of the old-fashioned ways that sea levels are kept from rising, is to have more ice. And Deborah says, in terms of the possibility of intentionally controlling climate, starting off with an ice age, what's the human responsibility for other life forms, in addition to our own life form? I mean, ice ages turn a whole lot of living landscape into pretty non-living ice. So what's our real responsibility to who?
Two good questions. I mean, first of all, we don't really want to invoke an ice age because
they're self-accelerating?
Yeah, they can lead to instability. A little ice age can become a big ice age. But also, I mean, that's like I think what we want to go for is something like what the climate's been like the last 10,000 years, which is it's actually been an interglacial, is what we call it, a little warm period in the middle of a larger basically, we're in the middle of an ice age, but we're in this interglacial, which is sort of a thawing within the ice age. But the idea of trying to restore some of the ice that we're now losing and dissipating in the around the Arctic is an interesting idea, and I have heard some proposals of that people have for these sort of solar-powered ice makers that we would. I'm not ready to go there yet, but I think I'm all in favor of people researching that. I think that we still haven't tried the obvious, which is just limiting our CO2 emissions by by changing our energy supply. But I think in terms of these more radical geoengineering schemes, I'm definitely in favor of people doing the research and knowing what our options are in case we need them. But I think it's foolish to jump into tinkering where you don't want the cure to be worse than the disease. We have to know what we're doing. We've got a lot to learn before we try some of these more radical interventions. As far as our responsibility to other creatures, that's an interesting one. I mean, there's the pragmatic issue that we don't want to cause wanton extinction even for our own self-interest, because we need other species. We need a healthy biosphere for agriculture, for biomedicine, for all these reasons. We don't want to live on a planet, And then, of course, there's the ethical and moral question of, since we're conscious and aware of our role, at least to some degree, then we, do we want to be the species that causes a mass extinction? And so, to me, the ethical and the pragmatic kind of merge there, where it's clearly in our interest, both so we can live with ourselves and so we can live well to safeguard the diversity of life on Earth, as well as safeguard our own future. I think the two goals really converge.
Questions here that relate to something which, when you said, can civilizations manage longevity? Can they do tens of thousands of years, hundreds of thousands of years? The mind starts to go, whoa, wait a minute, because Chloe asked the question, change seems to be speeding up. What does that look like in terms of this very long-term scale of longevity? And Sean asked, by the way, in terms of planetary intelligence, can the proliferation of artificial intelligence be the beginning of planetary intelligence? Artificial intelligence is one of the modes of speeding up of world-changing technology that we're talking about. So artificial intelligence at planetary scale and pace of change.
Yeah.
Does that either of those lead to longevity?
Well, it's a great question. And, I think with artificial intelligence, the honest answer about that is nobody knows where it's going. A lot of really smart people have a lot of interesting ideas about where that's going. I think it's legitimately considered to be likely, almost inevitably, to be a game changer in the 21st century. And the game changers are frightening, but they can also be, wonderful things. I personally am not a believer in the singularity, the moment of sort of techno rapture. I shouldn't say that here. I might offend someone.
It's okay if you say why. Why don't you?
Yeah. Well, no. I mean, it's quite possible. I say I believe that's a little too strong. I think that it depends on a certain model of what the brain is and what consciousness is and its relationship to the brain, whether you're just going to create a certain number of very fast processors in network with each other, and then you'll basically have a brain, and then the brain will even be better than our brains. That's possible, but it depends on a certain model of what a brain really is, or what consciousness really is, that I would say is unverified. But what I do think is equally possible is that our human, and is already happening, is that our human networks will become much better and much smarter and augmented and in partnership with the networked smart machines, and could actually potentially become that sort of missing link in our ability to globally have some coordination on the scales and in the ways that we need to sort of manage ourselves smartly. So I see it as equally probable that sort of a partnership of humans and machines could become that sustainable entity. I think in terms of evolution, you think of endosymbiosis, the forming of organisms by partnerships of smaller organisms. And the fact that we, of course, you can look at yourself, we are collections of bacteria, not just both because of our microbiome and because our cells themselves are collections of bacterial cells. And they are still within us doing what bacteria do, and I think being pretty happy. I could see us, with the aid of these machines, essentially becoming I'm not talking about the Matrix necessarily, or the Borg, although maybe I am, but maybe I am, but becoming, continuing to function and feel like humans doing what we're doing, but embedded within some matrix of smart machines that are kind of taking care of things in the way we need them taken care of. Mm-hmm. So it's a very hard question to answer, because it's one of these things that seems clearly to be accelerating and to be a likely game changer. And I've heard a lot of really smart predictions of what it's going to lead to. I read these books by Max Tegmark and by, what's his name? The guy that's much more pessimistic. Nick Bostrom, thank you. Yeah, Bostrom. And I read this and I go, yep, you could very well be right, but am I convinced that you really know? Nope. And that's basically my reaction to all of these. So.
Well, I'm intrigued by your bringing up sort of the microbial perspective. You sound like somebody who was bit at an early age by Lynn Margulis.
Absolutely. Yep. Another big influence. Yep.
Carl Sagan's first wife, in fact.
Yeah. And Lynn was a brilliant scientist, and she was right about a lot of things before
she was wrong about
before
it.
And then she was right again.
But the endosymbiotic, that these various creatures that were basically enemies that were eating each other, got inside each other and then became collaboratively much more powerful. So that we have mitochondria in every one of our cells that have their own DNA because they used to be another species, and she was the great proponent of that and the realizer of that. And every time I hung out with Lynn, I would get a sense that microbes, they're swapping genes all the time.
Yeah.
And, they're doing all this. They're doing. They're figuring out quorums and then acting on the quorums and making biofilms. And the intensity of the interaction that microbes have, we have yet to get to.
Right.
But what you were just describing sounds like we are on the path to getting to that level of interaction.
Well, I wonder if that's partly that's sort of my. I think I'll admit I'm sort of a congenital optimist. So I always search for the way in which things could actually be working out to our favor, and I am drawn to that analogy that we are as yet like a very crude assemblage of microbes that haven't really figured out how to do endosymbiosis yet. Mm-hmm. But the sort of connective tissue that we need could be our smart machine networks.
There's a transition going on right now from basically the accelerating power and power of digital code to now include the accelerating power and power of genetic code. And you're a biologist, an astrobiologist, but you're still a biologist. What do you make of all that?
Well, I think it's very exciting. It's another one of the things that's a little bit daunting because it's so powerful, and who knows what it could lead to. But it's kind of funny that in our attempt to come up with better and better digital storage and more efficient ways of encoding information, that like T.S. Eliot said, at the end of all our exploring, we come back to to the place we started and see it as if what we end up with after that is like, oh, DNA. That's how we should store information. It's sort of like DNA gave us these brains to develop all this digital technology and made us smart enough to like come back and go, oh wow, DNA is really good storage. So it is very intriguing that ultimately by hacking biology, we may empower ourselves more than just by inventing.
That sort of raises a related question, which hacking digital code doesn't seem to bother anybody. Hacking biological code seems to bother almost everybody. Why? What's the difference?
That's an interesting question. And maybe because the monsters that we can imagine are scarier than the monsters we can't imagine.
That's pretty good.
Right? You can imagine all kinds of like scary variations of biological creatures. We have no idea what a machine monster would even, be like. So, but you're right. I mean, maybe it's a kind of prejudice we have.
You're good, David. Dev, or maybe De Yaganuba, asks, given our current tools, what are our best techniques to detect bio-related epoch changes in extrasolar planets? And by the way, how about sapient epoch changes?
Yeah. Okay, so our best, there's a couple problems. One is just, even if we knew what to look for on exoplanets, how do we detect it because they're so darn far away and, getting any information. Just the fact that we've been able to determine that they're there is a huge breakthrough. And a lot of times that we can't even see them, we detect them indirectly because we see the wobble that they're moving a star around or something. So learning anything about exoplanets is going to be very hard. However, there's a new generation of instruments and a new generation of scientists. A lot of the people working on exoplanets now are young, really clever astronomers who are figuring out ways. I thought, when we first detected exoplanets, I thought, well, we're never going to know much about them. And of course now people are applying themselves and they're finding very clever ways by looking at the light from that star when it passes through the planet that's transiting in front of it and how, you can say something about what's in that atmosphere. They're starting to figure it out. So then the question is, okay, but what do we actually look for to find life? And a lot of it goes back to Jim Lovelock and Lynn Margulis, actually, and the idea that life creates disequilibrium. You don't want to be too geocentric and say we want to look just for oxygen or just for carbon-based life, because then what if it's doing something different? But the idea of looking for disequilibrium, that whatever life is, however life works elsewhere, it's going to create some chemical disturbance. It's going to use energy and change the chemical balance of its environment. So if you just look for weird atmospheric chemistry, for chemistry that wouldn't be there without something provoking it, then that something could be life. So that's sort of our main technique now, is to just start determining the atmospheric composition of exoplanets and look for mixtures of gases that seem to be not natural in the sense of not geological.
Okay,
and then
so what's weird? What's wrong with Earth's atmosphere that an astrobiologist from afar could detect that there's something going on?
If you were an astrobiologist in some other star system and you had a good enough spectrometer so you could look at the atmospheres of the planets in our solar system, you'd look at Mars and you go, a lot of CO2, that's kind of normal for a rocky planet. You look at Venus, you go, a lot of CO2, that's kind of normal for a rocky planet. You'd look at Earth and you'd go, whoa, check this out. You'd call your buddy over, you'd hit him on the back with your tentacle and you go, and Earth is flagrantly strange, its atmosphere, all this oxygen, and not just oxygen, but oxygen mixed with methane. Those are gases that eat each other. They don't coexist unless something is violently forcing them into the atmosphere. And in fact, if all the life on Earth died out, it would quickly revert to a Venus or Mars-like state. It would just be CO2. And so Earth's atmosphere is flagrantly disturbed by the presence of life.
How about before the oxygen catastrophe, though? How about when it was just abiotic? Or
Yeah.
Just,
Yeah, so then it was probably more subtle, the signs of life, but there was probably an excess of methane. You had methanogenic bacteria.
Titan has lots of methane.
Right. Well, Titan might have life.
But it's cold.
We can't roll that out yet. Titan.
Right.
That's one of the things that is to me is intriguing about Titan is why does it have all that methane? It shouldn't. So I'm being a little bit heretical here, but we have not yet explored Titan
Okay,
really
so you're
yet.
now debating with Carolyn Porco, who said in that chair last month that Titan is just too cold at 300 degrees Fahrenheit below zero for life processes for metabolism basically to have much of a chance.
Well, Carolyn,
But-
no, no. I mean, of course, these are the kinds of things that that astrobiologists wrestle with. What are really the requirements? Can we say that life needs a temperature range like we enjoy, or are we just being self-centered? Obviously, our kind of chemistry would not work on in the temperature range of Titan, but there are other kinds of chemistry that work well in those temperatures. So I think we have to be a little careful before we start declaring places off limits. To me, the only place that you can declare off limits is a place where nothing's happening. There's no energy, there's no chemical flow, there's no physical flow. Life needs some kind of flow, some kind of disequilibrium, some kind of exchange of matter and energy to sort of surf on and ride and thrive off of. So places where nothing's happening, to me, are pretty securely dead.
So Titan has an atmosphere, and in fact, you were describing to me before the show that it would be a great place to develop wings for people because there's very low gravity and very thick atmosphere, and you can fly.
Yeah, human-powered flight on Titan.
On the other hand, it has an atmosphere in Jim Lovelock mode. You look at the atmosphere, is there anything weird about it?
Well, yes, because there is an excess of methane on Titan that actually should go away in like a 10 million year time scale, because there's ultraviolet light and particles from Saturn's magnetosphere that are eating methane on Titan.
Okay.
And we don't know what's replenishing it. Now, the standard wisdom is it's cryovolcanoes and it's coming from the interior, and it could be. But if you're going to look at it from a Lovelockian perspective, you could also say, maybe we should just make sure there's nothing else going on Titan, because that methane's a little weird.
Okay, so here's a question so we're looking for the biological epoch transitions in other planets. How about the Sapiens transition epoch? Can you detect that from the atmosphere of different planets?
Yeah, so how would you identify another planet that had gone through it was in its Sapiezoic?
Right.
That's a really good question. Some people have said, well, let's look for carbon dioxide pollution. But I think that's a really bad idea, because that's obviously going to be a temporary problem. That's not, you want to look for some long-lived signature, some sign of a stable, the ones that you're going to find are the ones that have some lifetime. So what I would look for is the signs of a planet being managed somehow, a climate that is not being left to its own devices. For instance, as we spoke about, if we're going to be here for another 100,000 years, we probably would mess with the cycle of ice ages. So how would we do that? One way is by introducing chemicals like CFCs into the atmosphere, not CFCs themselves, because they destroy ozone, but there are other artificial atmospheric gases that are very powerful greenhouse gases. So if you see some synthetic gas that seems to not be natural that's affecting a planet's climate, you see the spectrum of something like that, you go, Or, in a more general sense, over the very long run, stars heat up and the habitable zone moves out. So if you see a planet that looks as though it has a climate that is preserved from an earlier epoch in that solar system's history, you might go, somebody's been kind of messing with that planet's climate. So I don't want to try to second guess the aliens too much, because I just think, but I think that as we look for biosignatures, which is what we're starting to do, we should also be on the lookout for technosignatures. If we start to see weird atmospheres, we should at least consider that as one of the causal agents.
How weird can life get? I mean, it's pretty weird.
That's a great question. Yeah,
the range here, extremophiles and all this kind of stuff.
That's a great question. Because as astrobiologists, we have this sort of nested set of assumptions that we make, and we really don't know how good any of them are. We often assume that life needs carbon and water. Now, maybe it does, because that's certainly a good way of doing it, and people haven't imagined fully other ways of doing it. But maybe that's just looking for our keys under the lamppost, searching for what we under the light, searching for what we know. And maybe the reason why nobody's imagined another fully realized system of biology is because our imaginations aren't good enough. Nature has a way of solving problems that, you know, we tend to learn things through exploration, not through imagination. This is true when we explore the solar system. We didn't think there were going to be volcanoes on Io until we got there. In fact, we knew why there couldn't be.
We thought there were going to be canals on Mars.
That's right. And when we get there, we figure out why what we knew couldn't be there could be there. We come up, you know. So I suspect it'd be much the same with life. So we assume it has to be carbon-based. Maybe it doesn't. We assume it has to be chemical. Maybe it doesn't even have to be chemical. Maybe in a more general sense, any kind of physical process can create, on some scale, self-perpetuating structures. We really don't know how weird life can get. My hunch is that there are at least other chemical systems for life that have nothing to do with carbon.
How about other forms of habitability? Freeman Dyson imagines that, we assume that rocky planets are the only place that life can be, but there's a whole lot of different kinds of environment in space, and different kinds of life could live there.
Absolutely. Well, Carl Sagan used to talk about. Carl Sagan used to talk. He imagined this whole ecology on Jupiter of the floaters and the sinkers and the gas bags and the. You know, I in my view, any place where there's interesting chemistry, and by interesting I mean flows of disequilibrium, chemicals that can react together and produce energy, which then can produce structures, is a possible habitat. And I think that as we explore further, we'll be surprised. Just as we've been with the geology. You know, we just got to Pluto. We as far as we knew.
Tell us about Pluto. What was surprising and weird about Pluto?
Oh, Pluto.
Pluto.
It's a great example of how when we explore, our preconceptions are busted because it's so far from the sun. There's no energy source to drive geology, and what fooled us with the moons of the outer solar system, we thought, well, there can't be geology on these cold icy balls, but there were because it's all tidal. You know, the moons of Jupiter are getting pulled around in Jupiter's gravitational field and interacting with one another, and that creates these tidal energy sources. But Pluto doesn't have anything like that. It has a moon, but there's no tidal interaction like that. But we get to Pluto, and it's full of interesting geology and glaciers that are flowing and surfaces that are young and changing, and it's because it's doing it with other kinds of materials, and we didn't imagine. Nitrogen here on Earth is a gas. We're breathing it right now, and this is mostly nitrogen, this air that we're in. On Pluto, nitrogen is a solid, and there are glaciers of nitrogen flowing down mountains of solid water ice. So, and at that temperature, nitrogen is actually kind of squishy and volatile, and it doesn't take much to move it around, and it's convecting. It's, with a little meager amount of energy coming from the radioactive decay of the rocks inside Pluto, it's causing nitrogen convection and glaciers to flow. So this is all by way of saying that, every time we expect a place to be uninteresting, it's because it's our perspective of not being able to imagine what nature's doing out there. That's true about geology. Now, if I had to guess, it will also be true of biology.
Here we go. Thank you very much.